Hey, so I recorded this damn thing for 15 minutes and it turned out this new headphone I have has some loose connection with the jack in the computer, so it's a nightmare. I have to redo it, but that's life. What can you do? Okay, so let's read the summary now, which gives us a chance to discuss a few additional points. Essentially, the review has highlighted the evidence for a modified paradigm of the interactions of various modes of specific decadal variability and how the important mechanisms at play in the ocean atmosphere system basin-wide may yield this variability. So we need to find the energy that is giving us this spike at lower frequencies, and whether they are arising out of the tropics or extratropics, or there is a cycle that goes on between the extratropics and the tropics. Of course, there is an interaction going on. The dominant statistical modes of basin scale PDV, such as the IPO and TPDV, are linked and explain a large fraction of the global low frequency variability in SSTA, as we saw before. But you can expect that Pacific is the largest ocean. It's got a lot of ability to hide away the heat content, and has ENSO in the tropics, which has global reach. So the decadal variability cannot stay within the basin. It has to reach out to the global scales. So in that sense, remember, we are calling these statistical modes of PDV because that's what they are. We haven't explained whether they are, uh, you know, real dynamically coupled mechanisms, or they are just interacting modes that manifest in statistical patterns that we are looking at with various methods like EOFs. And the best we have done here is to take the linear inverse model and try to diagnose the various modes and their interactions. But still, a lot is learned, but a lot more questions remain in terms of what needs to be understood. So the extratropical SSTA pattern of PDV over the North and South Pacific, variously defined as the PDO, SPDO, NPGO, NPMM, and SPMM, are also linked to the global SSTA decadal scale variability. Obviously, their patterns can be explained to first order by reddening of the atmospheric forcing that arises from a shift and or intensification and weakening of the atmospheric mean circulation's pressure systems. So you have these subtropical pressure, subpolar pressure systems, and you have the competition between polar high pressure and subtropical lower pressures relatively, and there is a battle through the jet stream. So you can have the ups and the pumping up and pumping down of the trade winds, which can result in ENSO, or you have pumping up and down, or the shift of the jet stream and the westerlies, and the ocean is basically integrating everything and producing these low frequencies. Right, so at low frequencies, all atmospheric mean circulations pressure systems are involved, in terms of intensification and weakening and stochastic integration. At low frequencies, all statistical modes of Pacific climate converge into an ENSO-like pattern of TPDV, highlighting the important role of ENSO dynamics as a bridge to establish the basin scale PDV. So to the extent that there is always a trade wind system, there is always upwelling in the east and warm pool in the west, and there is always recharge discharge. Can you have recharge discharge at interannual timescales with ENSO and a decadal timescale recharge discharge, which is related to these interactions that we are talking about? Sorry, I don't know how much noise that made into the recording. I will check. While the description of PDV from the statistical modes is useful to track the state of Pacific climate and its impacts on weather and marine ecosystems, it does not explicitly resolve the dynamics of atmospheric and oceanic teleconnections or the coupled feedbacks which are important for understanding PDV. Okay, what do you do? For this reason, we used the LIM climate diagnostic toolbox for PDV, which is served here, to empirically reconstruct the dynamical operator of Pacific climate and its eigenmodes using a reduced observation space. After extracting the leading LIM eigenmodes from the three reanalysis products, HAD-ISST, NOVA ERSST, and ORAS4, we show that the spatial patterns of variance of PDV, such as the IPO, PDO, and TPDV, result from the interaction of the two lowest frequency dynamical eigenmodes, namely the Kuroshio-Oishio extension and the NPCP eigenmodes. The spatial structure of these two eigenmodes is basin scale and depicts that the two-way teleconnection dynamics between the tropics and extratropics associated with the sequence of ENSO precursors to ENSO in the tropics back through ENSO teleconnections to the extratropics are the fundamental mechanisms to energize and synchronize the basin scale footprint of PDV. Okay. More specifically, the NPCP eigenmode captures the interannual to decadal scale variability and energizes the variance of the NPO, NPGO in the extratropics to central Pacific ENSO in the tropics and back to NPO, NPGO in the extratropics, as we saw in figure 6 that you can go back and look at. The KOE eigenmode exhibits a basin scale structure that resembles the IPO and is characterized by decadal to multi-decadal timescales. It tracks the two-way teleconnections of the KOE with the central and eastern North Pacific associated with the propagation of the Rossby waves into the KOE. So North, East Pacific, Central Pacific do something that sends off a Rossby wave. The AFC interactions in the Kuroshio-Oishio extension then can travel back in the atmosphere to the east. Okay, so it tracks the two-way teleconnections. It tracks the two-way teleconnections of the KOE with the central and eastern North Pacific associated with the propagation of Rossby ocean waves into the KOE and the air-sea feedback response of the KOE onto the downstream atmospheric circulation of the North Pacific. This downstream response couples the KOE mode in the west as the eigenmode to the NPCP by activating the ENSO extratropical precursors and leads to a multi-annual preferred timescale of variability linked to the sequence KOE to NPO to CP ENSO to NPO NPGO to back to KOE. Okay. Although NPCP mode emerges as an oscillatory eigenmode, its period is much longer than its decay timescale. You can look up the table for that. This implies that it is unlikely that a sustained oscillation of this eigenmode will ever be observed. Therefore, while eigenmodes capture the dynamical sequences summarized here, these sequences will only be predictable over some finite period until they eventually become entirely obscured by noise events that are largely unpredictable. So, have high frequency weather noise, which is integrated to produce low frequency signals in the ocean and the coupled climate system with global reach, but they have a decay scale because the noise forcing is continuous, right? Well, this synthesis has highlighted some of the dynamical modes and mechanisms of PDV across various reanalysis products. We must recognize that these observational sources are still relatively short in total period of record, which introduces some uncertainties in our ability to cleanly resolve the modes and diagnose their mechanisms. It also remains unclear how non-stationarity in the data and in the projections of future climate influences the expression of the dynamical modes. Furthermore, we have shown through stochastic simulations of the LIM that different realizations of specific climate from the same dynamical operator can lead to substantial differences in the relative importance that each mode plays in explaining the statistical patterns of PDV, such as the PDO. Acknowledging and quantifying this range of uncertainty is critical for analyzing and comparing Earth system models and assessing the significance of changes in the PDV dynamics related to anthropogenic forcing, which we have not addressed in this review. Future studies may want to use LIM diagnostics approach to explore PDV in a changing climate. So basically we can go back to this figure and see that LIM allowed us to do these ensembles to look at the relative contributions of KOE, NPCP, and EP, and so to PDV, right? So in that sense, so this reconstruction of PDO. So you can see that depending on the various perturbations to the ensemble members, you can get different contributions from these three modes, which are the most intrinsic basic modes. Then you want to see how each mode is responding to anthropogenic forcing. And so itself is changing. There's some argument that CP and so may be becoming more predominant, but how is that related to KOE and NPCP individually and with their interactions and their interactions with ENSO and so on. So it's a very convoluted, complex dynamical feedback system with decay scales so that the noise always keeps coming back. So the predictability itself may be short, and yet it is very important because decadal timescale predictions, the societally relevant timescales, are very critical because the projections out to 2100, in my opinion, have you know, some limitations because the projections beyond a couple of decades are completely dominated by the uncertainties in the scenarios themselves. So decision horizons of a decade are very important for water, food, agriculture, transportation, energy, health, and so on. So decadal predictions and understanding decadal variability is very critical, and specific decadal variability is very critical because it dominates the global decadal variability as well. Monsoon, for example, has a decadal variability, but is that really independent of PDO? Is it also feeding back with these uh, KOE and NPPs, NPCP and ENSO? We know that monsoon and ENSO are an interacting system, so you expect that monsoon decadal variability must have something to do with these interactions as well. And monsoon itself is responding to climate change also, and it has an intrinsic time scale of intraseasonal variability. So if ENSO is intraannual variability with CP, EP, ENSOs, and it has interactions with decadal modes, and it has interactions with, with the monsoon. Monsoon has an intrinsic time scale at intraseasonal time scales. Then you have basically a full multi-time scale system, and we have to understand how each one work works in a natural variability mode and how they're all responding to climate change. For example, all the ENSO, global warming, Arctic forcing, Antarctic forcing, everything seems to project onto the duration, intensity, and frequency of the active and break periods or the mesos in the climate system. So that time scale is important, just like the PDVs seem to project onto some, uh, you know, some pattern that resembles ENSO in some way with different meridional scales. So maybe there are fundamental time scales at high frequencies that result in low frequencies, and they all interact with each other, but they are still projecting back onto some intrinsic modes like the intraseasonal variability and ENSO. Okay, so I added the monsoon part just to say that that needs to be considered as well in these decadal variabilities. Okay, so I will leave it here, and the nice long paper with lots of references. Even though I have three podcasts, it is still very brief compared to the details. The main point I would like to convey is that I'm giving you an introduction to the complexity of this problem and the large number of open questions. So you must go back and read to make sure that you get what you want out of this. Okay, so see you in the next topic.